Today, let me introduce Lyapunov optimization. My name is Jungwon Kim, and I'm at Korea University. In general, in communication and network problems, we always try to do utility maximization. For the problem solving, we usually use linear programming, convex programming, and so forth. But for the problem solving or optimization, we do not have consideration for time in general. Then what if our solution introduces delays? Then it will be very harmful for real-time mobile systems. That's why we need to think about the trade-off between utility and delay. For the formulation, we are using Lyapunov optimization. And then the Lyapunov optimization has two steps. For the first step, we have to do the time modeling. The time modeling is usually done by queuing system. And then based on the Q values, we are using Lyapunov drift in order to mathematical modeling. For the second step, we are doing time average optimization on the Q stability. It can be illustrated as follows. Here, we have trade-off between delay and utility. In delay modeling, we are using Q. In utility optimization, we have several examples here. The first example is energy efficiency. It can be on utility in general mobile systems. Or we can think about the quality maximization in video streaming. In addition, PSNR can be another index for utility for video streaming. Lastly, in learning system, accuracy maximization can be another index for utility. So in order to optimize these criteria in utility, we can think about the delay as well by using Lyapunov optimization. So here we have one example. Suppose that we have one smartphone here, and inside the smartphone, we have one processor. And then we have task queue inside. So when we touch our smartphone, we activate our Facebook, YouTube, and so forth. Then we are generally making some task in order to execute the applications. And then the execution will be randomly arrived. That's why the arrivals are random. And the task will be inside the queue. This queue is called task queue. And then if we allocate more and more powers in processor, then the processing can be accelerated. That's why when we allocate more and more cores here, then it will be very helpful in terms of stability because we can accelerate the processing by allocating more and more cores here. However, by activating more cores here, we have to consume more and more energy. That's why it's not good in terms of the energy efficiency. On the other hand, suppose that we allocate less cores. So in that case, it's not good in terms of stability. However, it is good in terms of energy efficiency. So here you can observe the trade-off between utility and stability, where the utility is defined as energy efficiency. Now, in this case, you can confirm that Lyapunov optimization can be used in this system. It can be mathematically modeled as follows. Here, we want to minimize our objective function. So, for example, we want to do the energy consumption minimization and so forth. If you want to maximize our objective function, then you can put the negative in front of this equation. This equation has bar on top of this variable, which means that we want to do the time average computation. So as you can see in the right-hand side, in y sub o, which is objective function, we are doing the summation for time steps, and then we are doing the average while the time goes infinity. That's why this is time average optimization. And then our basic constraint is that we have to guarantee the Q stability. That's why this means that we want to do the time average optimization subject to Q stability. As I told you before, the Q stability can be modeled by Lyapunov drift based on the queuing theory. Then eventually, with the constant gap optimization, then we can introduce this final form of the result. This is also called deep drift plus penalty. That's why this is also called DPP. And then we want to minimize this right-hand side function. So here, this function can be divided into two parts. The first part is for the objective function. The last part is for the stability. So in this function, the objective function can be determined by alpha of t, which is the action at time t. And then V is kind of constant trade-off factor between the utility and stability. In the right-hand side here, you have Q of t, which means Q backlog size in the system. A of alpha of t means arrival depending on our action at time t. And then B means the departure at the Q when the action is alpha of t at time t. So here, we can introduce both of utility and delay in a single equation. Suppose that our Q is empty, then in that case, Q value becomes 0, and then these part will be disappeared. And in that case, we can focus on our objective function. It means that if our queuing system is very stable, which means that Q is 0, and then we can purely focus on our optimization objective criteria. However, suppose that Q is infinite. In that case, this part will be more focused rather than our objective function. That's why we have to focus on the control of the stability. That's the main concept of Lyapunov optimization. By solving this single closed form equation every single time, depending on Q backlog size, we can introduce our optimal action in time average by solving this low complexity closed form equation. That's the basic idea of Lyapunov optimization.